Hello, folks. Here Luis again. Today I'm going to talk about one of my favorite calculus 3 topics. Today we are going to talk about line integrals in vector fields specifically. I'm going to explain very quickly line integrals on scalar fields, but this today's class is mainly focused on vector fields. Well, uh, what what happens with line integrals in vector fields? Let's imagine you have a three-dimensional. Wait a minute. I think I should draw it like this. Let's say, imagine this is three-dimensional. This is the z-axis. This is the y-axis. This is the x-axis. I mean, that's c. This is the x-axis. And first, you might remember the in single variable calculus that, for example, here we have this line, right? And how the way to get the area under this line is by integrating the function that gives us this line, right? Let's say this is fx. So, and this is, we want to integrate, let's say, from this point A from to this point B. So to get this area, this area, we would do it as follows: from integral from A to B of f of x dx, and that's easy, right? But the way we calculate line integrals, it's more similar to how we calculate the arc length. Maybe you might remember the next formula. S equal from is equal to the integral from a to b of a square root of 1 plus y prime squared dx. And this one, instead of the area under the graph, is going to tell us the arc length, this one, the one I highlighted with red. It will tell us the length, the arc length. And today I'm going to explain in scalar fields, the line integral basically tells us the area under a line that is given by the a certain parameterization. So, for example, let's say we have f x y equals x, not x itself, but p x y. Yes, but the thing is that since they're parameterized, I'm going to write it like this. And let's say well, basically like that. I'm going to leave it like that. And so imagine here we have this line, and we want to get the area under it, right? The f of xy will tell us the height, and how can we get like the path that is following in the xy axis. So let's call this like line. It could be like curvy, but I'm going to learn it like this. Let's say we zoom in on this line, and let's say here we have this line like curvy, right? And this is let's say this is S, but see, here we have the x-axis, and here the y-axis, like zoomed in, remember. And let's say here, to approximate, we can say this is a small change in S, and we can create a right triangle to get this small size in an S. So we have to, now have, sorry, ds dx, and here we have dy. So by Pythagorean theorem, we can set dy squares plus dx squares equals ds squares. But rather than, I said d, but this is delta. Well, rather than delta, we have a small change. So instead of delta, we have a differential. So dy squares plus dx squares, dx squared equals ds squares. And remember that dx and dy, dx and dy, y and x are on function of our parameter t. We had this, right? And so let's say, well, let's divide both sides of the question by dt squares. So now we have dy squared dt squares plus dx squares dt squares plus equals ds squares over dt squares. Now let's take the square root on both sides. So we have ds over dt equals square root of dx squares dt squares plus dy squares dt squares. Now remember, the line integral tells us the area under the line. So in order to get that, we are going to set the next integral, the integral from a to b of our function f x y, which tells us the direction. And do you remember what I said about the arc length and the integral? Well, basically, when in one single variable calculus, well, it's basically the same idea. So instead of dx, which was the axis where we used to integrate with respect to on one single variable calculus, we are not using that dx of this one, which was prime and dx. Instead of this dx, we are going to use ds. So here we have this times ds. But how can we get that ds? So multiplying on both sides, we are going to get we are going to get ds equals square root of dx squared over dt squared plus dy squared over dt squared times dt. So this is equal to the integral from a to b of x squared, of f of x y times ds, but ds is this, so times square root of dx squared dt squared plus dy squared dt squared dt. And that's basically how you how you how you can compute a line integral on a scalar field. So in this video apparently I took so long, so I'm going to make a second part on purely vector fields, but you got the idea, right, of line integrals on vector fields. The line integral is basically the area under the line given by the path that is given by whatever parametrization you are doing. Well, and that's all. I'm not going to solve a problem on this because this is basically just a deduction of the formula of line integrals on vector fields. So see you next time.